Good morning students, welcome to the mass transfer course. Today will be lecture 20. Here we are discussing about the interphase mass transfer. Today will be the last lecture. So in interphase mass transfer we have seen how to calculate the overall mass transfer coefficient based on gas phase or based on liquid phase. These are capital Kx, capital Ky accordingly, and thereafter we made the material balance for four systems: steady state counter current, steady state co-current, then steady state cross current, and thereafter we have seen how we can construct multiple stages in a single column. Multiple stages. There are three. And for that one, we have seen what are the different types of operating lines. So today we'll solve two problems. One is based on the cross current mass transfer, another is steady state mass transfer in stage wise contact with two phases. So problem 1 is cross cutting. 100 kilogram of an aqueous solution of p-chlorophenol at a concentration 1 gram per kg of water is to be treated with 2 kg of an absorbent to recover the compound from the solution by a two-stage cross-current contact. Okay. So we have a para-chlorophenol, the concentration is 1 gram per kg, okay, and we have 100 kilogram of this aqueous solution, okay, that concentration, and now this 100 kilogram aqueous solution I want to treat with 2 kg of absorbent to recover this compound from this solution. Calculate the maximum percentage recovery of the solute if the equilibrium relation at the operating temperature at 290 K is given by capital Y into equal to 0.6x, where x kg solute per 100 kg water and Y is kg solute per kg absorbent. Okay, so for this one we have to calculate what are the percentage of recovery in two-stage cross current. So this is my problem. Now here if you see the equilibrium relation is very important, interesting. X is kg solute per 100 kg, 1000 kg water, and Y the kg solute per kg. So if you see that concentration X and Y, here it is per 1000 kg and here it is per kg. So that way it is given. So I need to correct this in a same way. Okay, I should have a kg per kg, or if it is kg per 1000 kg, here also I should express kg per 1000 kg. Or if I express kg per kg absorbent, then x also should be a kg per kg of water. So that change I need to make here. So let's do first one this. So x is the solute of concentration in kg in water, that is kg water per 1000 kg water. So if x dash, let's take kg solute concentration kg per kg water. Okay, so Then what will be this? If it is kg per kg, then in 1000 kg, that will be into 1000. So x dash and x relation will be this. Now equilibrium relation is y equal to 0.6x. Now y equal to kg per kg. It is kg per 1000 kg. So I will replace this in here. This. So this into 1000 into x dash. So this is y equal to 600 x dash, where y also kg per kg absorbent, here x dash equal to kg per kg water. Okay, so now it is this equilibrium relation has a unit constant. Okay, use equal amount of the absorbent 1 kg each in 2 stages to achieve the maximum recovery of the solute. Since the equilibrium relation is linear, this is the relation, it will be convenient to solve the problem algebraically. I can solve this algebraically, or you can do it. So feed is 100 kg, okay, and solute concentration is 1 gram per kg. So x0 will be 1 by 1000. Okay, so that is equal to 0.001. Now what will be? This is the what will be LS? LS will be 100 total solution. 1 minus 0.001 equal to 99.9 kg. Okay, so this is will be my LS. Okay, and GS will be 1 kg because I use the pure absorbent, and that is will be my GS1 GS. That. Now material balance LS into x0. X0 is entering, outgoing is x1 dash. Okay, equal to GS into y1 minus y0. Now I know x0 is known to me. X0 is this. Y0 is a fresh absorbent. This is now in a this is liquid extraction. So, but when it is coming out from the extra y1 and x1 dash, these two are in equilibrium, isn't it? So I will use the equilibrium relation for this. So point LS equal to 99.9 into 0.001 minus x1 dash equal to 1. That y1 equal to this equilibrium. I will put this one. This is the my equilibrium relation. Okay. This minus this. So that corresponds to x1 dash equal to 1.427 into 10 to the power minus 1. This is for material balance. So this is the concentration is coming out from the water stream. Now it will enter into the second. So this is the input, and output will be, let's take x2 dash ls, same ls, gs. Okay, this will be, it will give the y0 because cross current, same y0, and it will be y2. Let's take for same. Now here also again this y2 and x dash 2 will be with equilibrium. So I will put this one again. So ls x dash, this is the concentration I got, x dash 2 into 1 600 x2 dash 0. So x2 will be this. So solute, this is the outlet. So solute living with the solution with stage 2 equal to ls into capital X dash 2 dash equal to 99 point this into this 0.002035 kg. So fractional removal equal to what? 1 minus this by total what is this? 99 into 0.001, 99 point this into 0.001, this into 100, this is correspond to 90%. So now you see this parachlorophenol is 1 gram per kg in 100 gram water. and I am using only 100 kg water. Okay, and I am using adsorbent only 2 kg, and then things are coming. So if you understand, from 100 gram solution, 100 kg solution with 2 kg absorbent, I am getting 98% recovery. Okay. So this is that is problem related to a cross cut. Now let's take another problem related to determination of ideal number of stages in a tray column. It is required to absorb 95% of acetone from a mixture of nitrogen containing 1.5 mole percent of the compound in a counter current tray tower. Okay, in a counter current tray tower, okay, nitrogen with acetone is going from the bottom to top with 1.5% acetone. Okay. The total gas input is 30 kilomole per hour, and water enters the tower at a flow rate of 90 kilomole per hour. Okay, from the top, it is water is 90 kilomole per hour. The tower operates at 100 K and 1 atmosphere. The equilibrium relation is y equal to 25x. Determine the number of ideal strays necessary for the separation using graphical method as well as Crimson method. Okay, so this is the last day what we discussed. We solve this problem. So here I will you do the graphical method. You do it at your home. What way we discuss. Okay, I tell what will be that if you get the extreme 2 points, then you can make this LSGS. Okay, so then corresponding you can do it. Okay? And today we will see the how to make it in Crimson. Calculation of flow rate at 1 hour basis. Okay, so Gn plus 1 30 km and Yn plus 1 equal to, if you see, this is the thing. So gas is going, this is nth tray, this is tray, so G1 Y1 Gn plus 1 Yn plus 1, and this is L0 X0, this is Ln X. But keep it in mind, here I am taking the concentration in terms of mole fraction. Okay, but you can take in terms of our mole ratios. But I am telling when the solution is dilute, because it is 1.5%. In case of dilute solution, mole fraction and mole ratio, if you calculate make the calculation in terms of mole fraction, and then again if you do the calculation in terms of mole ratio, you will see that there won't be much difference. So in case of dilute solution, because here is, if you see, that is 1.5%, it is very dilute solution. Okay. So in this case you can adopt either of these, result will be almost same. But here I am doing with the mole fraction. You make this calculation in terms of mole ratio, then you see what is the difference. Okay, that you will do. So moles of acetone entering 30 into 0.0, this is the thing. So then what will be GS? GS will be 30 minus 0.45, 29.55 GS. Okay, that will be, that also you can. 95% of the solute is absorbed. So then kilomoles are leaving. What is leaving? So 0.45 entering. Then because 1 hour basis, 1 minus 94. So this is this mode is. The equilibrium is relation is yx. That is in terms of mole fraction. But when you calculate the in terms of mole ratio, then again you have this equilibrium relation you have to convert into capital Y, capital X. Okay, that you need to do it. Okay, The concentration or low dilute solution, so Kremser equation can be used to calculate the number of trays. It is advisable to use the average absorption factor. So flow rate of exit gas, what would be this? This is the carrier plus this will be solute. So carrier will be 30 minus 4 pi plus G1, this solute will be this one. So this will be the exit. So that will be the 29.5 kilomole. This is our G1. Gn plus this. Okay. Similarly, L0, L will be 90 L0. Okay. And outlet will be 45. This whatever the thing it will come to here. So this will be this. So absorption factor at the top will be what? L0 by mg1. So 92.53. This is, and bottom that ln mgn plus 1. So 90.43 divided 2. This is the m. It is same by 30. So 1.191. You see there is little bit different. Okay. Why? But if concentration would be high, then this difference would be high. So I will take the adsorption factor, what, either top or bottom. Instead of let's take the average of this. I will take the average of this. Now I will take the calculator n, because absorption, this is the formula. Okay. And when you calculate the mole ratio way, then you have to get capital. Okay. So these are things. So now it is coming, if you put this value, then it is coming that 7.8 number of stages. 7.8 means 8. So these are the thing, and you can construct this graphical method. If you see one example in BK Datta 4.6, it is given. Accordingly, you calculate the number of stages required, ideal stages required. You will see it will be almost means. So this is all about our interface mass transfer. See, if you, so still now we have completed only 4 chapters. In first chapter, that was introduction, okay, and motivation part. Second chapter was molecular diffusion. Third chapter was convective mass transfer and mass transfer coefficient. In third chapter, we understand how to calculate the mass transfer coefficient. Okay, because in mass transfer coefficient, everywhere you require in your calculation. So how to calculate the mass transfer coefficient, that we have learned in chapter 3. And chapter 4 is the more conceptual chapter. If you understand this chapter 4, then you will see remaining all these processes are the application of chapter 4. Here, that's why I am telling here also, although I am taking the example of absorption, but it is applicable for any 2 phases, L phase and G phase. It can be solid liquid, liquid, gas liquid, whatever you take. And as we know, according to different phases, different processes are there. Absorption, distillation, humidification, adsorption, leaching, all these things are the what is the interaction between 2 phases. And this, and every time you will see there are only 4 types: co-current, counter current, cross current, and multiple stages. And whatever theories we develop now, we'll just apply these theories for a particular thing. So I will request all of you, you study this chapter very mildly, whatever discussed in the class, means in lecture notes. You, along with this, you should study both the books, both BK Datta and Trevor. You should study both the books. Along with, you solve all the problems of Trevor and BK Datta, and you will see in mass transfer you will not face any problem, even in GATE exam. But take, sometimes people think, okay, GATE is 1 or 2 1 year later, we will study before that. See, GATE studying in 1 month or 2 months or 6 months you cannot crack the gate. You can crack the gate once you learn the subject when the course is going on. If you learn the mass transfer now, okay, then only you can able to answer the gate questions on the mass transfer. Otherwise you will not, because concept within 1-2 months concepts will not grow. So thank you all, and next we will study that mass transfer equipments.